ఇంకా పిల్లల్ని కావాలంటే మీరు మీట్ చేయొచ్చు, ఓపెన్ ఉండంటే ఉండనియండి, మీ ఇష్టం.
Okay.
లైవ్ స్టార్ట్ అయింది బై, కెన్ స్టార్ట్.
Okay. Sure. Just a few seconds.
ఓకే, ఆటోమేటిక్గా రికార్డ్ అయిపోతుంది. ఇంకా మీ పిల్లల్ని మీరు కావాలంటే యూ కెన్ మీట్, యూ కెన్ అన్మ్యూట్. పిల్లలకి ఆప్షన్ కావాలి.
Is it visible, students?
Yes, sir.
ఇక్కడ చిన్న కనపడుతుంది.
Okay. జూమ్ చేస్తాను. అంటే పేజ్ వైజ్ రాశాను బై ఇది.
ఓకే ఓకే, రైట్. స్క్రీన్ ని పెద్దగా సెల్ లో చూసే వాళ్ళు చెప్పండి అన్న. ఇజ్ ఇట్ ఫైన్?
Fine, sir.
Okay, fine, sir.
రైట్ రైట్.
Okay.
బై క్యారీ.
Okay, thank you. So you know chemical reactions which takes place in both directions. Some reactions takes place in one direction and some reactions takes place in both directions, that are called reversible reactions, which means forward step as well as backward step takes place for some reactions. So that examples we'll see later. And whenever there is a reversible reactor, which means forward reaction as well as backward reaction, and there after some time there exists an equilibrium. So which means the rate of forward reaction equal to rate of backward reaction. At some point the rate of forward reaction becomes equals to rate of backward reaction. So for this reversible reaction at equilibrium, we apply law of mass action. The rate at which a substance reacts is proportional to its active mass, and the rate of a chemical reaction is directly proportional to the product of the active masses of the reacting substances. So this is a statement of law of mass action. Either we take in terms of active masses, or we can also take molar concentration. The rate at which a substance reacts is proportional to its active mass, and the rate of chemical reaction is directly proportional to the product of the active masses of the reacting substances. So according to law of mass action, assuming that active masses are equivalent to molar concentrations. So see, for this general reaction, AA plus BB, and this indicates equilibrium, which means the rate of forward reaction equals to rate of backward reaction. So normally for a reaction we will mention with one arrow mark. If both directions takes place, two sides arrow marks, and this off-headed arrow marks indicates equilibrium. So the rate of forward step for this reaction is equal to Kf into concentration of A to the power of A and concentration of B to the power of B. And similarly, the rate of reverse reaction or the backward reaction, Rb equal to Kb into m to the power of m where M is the product, N is product, and their coefficient small m, small n. Simply we can write Rb equal to Kb into m to the power of m, n to the power of n, isn't it? And here at equilibrium, so what we are telling that the rate of forward reaction is equal to rate of backward reaction. So we can equate these two equations. Kf into a to the power of a, b to the power of b equal to kb into m to the power of m, n to the power of n. So that we can modify this equation as like this: kf by kb equal to k equilibrium equal to m to the power of m, n to the power of n, and a to the power of a, b to the power of b. Okay, is it clear? So what we can say that the equilibrium constant, the product of concentration of products by product of concentration of reactants, and their coefficients becomes their powers of that concentration. Okay, is it clear? So this is law of mass action. And the constant K equilibrium is called equilibrium constant. And that equilibrium constant we can write in terms of concentration, or in terms of partial pressures, or in terms of mole fraction. So for any reversible process, any reversible system, we can write in terms of concentration, or in terms of partial pressure, in terms of mole fraction. What is that? Equilibrium constant. And as we have seen in earlier slide, Kc equal to m to the power of m, n to the power of n, divided by a to the power of a into b to the power of b. And in terms of partial pressures for gases, so partial, if they are gases, the reaction mixture, the reactants or products are gases, so we can write their partial pressures. Pm to the power of m, Pa to the power of n by Pa, that is partial pressure of A to the power of A, and partial pressure of B to the power of B. And in terms of mole fractions, mole fraction is one of the expressing the concentration of solutions. Mole fraction. Yes, any doubt? Mute చేసుకోండి అమ్మా, ఎవరైనా డౌట్ ఉంటే అన్మ్యూట్ చేసి అడగండి, because for others it will be disturbing. So Kx equal to xm to the power of m, xn to the power of n, divided by xa to the power of a, xb to the power of b. So these three are important relations. Remember, or you can note down. And we can relate the equilibrium constant with delta Z0. So what is delta G? Any one of you respond?
Gibbs energy. Change in Gibbs energy.
Change in Gibbs energy, sir.
Good, good. Change in Gibbs free energy. And change in Gibbs free energy in standard conditions equal to minus RT natural logarithm Kp. This is another important equation, relation between change in free energy and equilibrium constant. And the relation between Kp and Kx. So you have to remember all these equations, because so we'll apply these equations whenever required, that is in a numerical problem. So Kp equal to Kx into P to the power of delta n. Kp is the equilibrium constant in terms of partial pressure, and Kx is the equilibrium constant in terms of mole fraction. And here delta N is M plus N minus A plus B. That is total number of gaseous products minus total number of gaseous reactants, isn't it? And P indicates total pressure. Then coming to the relation between Kp and Kc. So you know something about this equation. Kp equal to Kc into RT power delta N. And it also relates, the Kp Kc relates with the temperature, absolute temperature, isn't it? So we can relate the equilibrium constants with the absolute temperature and delta N. So what is delta N? Any one of you?
Change in number of products minus number of reactants.
Number of gaseous products minus number of gaseous, number of moles of gaseous products minus number of moles of gaseous reactants, gases only. Okay, up to here it is clear?
Yes, sir.
Law of mass action and equilibrium constants in terms of concentration, partial pressure, and then mole fraction, and then the relation between Kp, Kx, Kp, Kc. So the derivations are not required, but you remember the equation so that we can apply in a problems, numerical problems, whenever they come. And the equilibrium reactions can be classified depending on their the physical state of reactants and products into two categories, that are homogeneous equilibria or equilibrium reactions, and another one is heterogeneous equilibrium reactions. So let us discuss one by one, that are number of products molecules is equal to number of reactant molecules. So take this example. N2 plus O2 gives 2NO, that is nitric oxide. The formation of nitric oxide from nitrogen and oxygen gases, which is a reversible reaction, and all are gases. So 1 mole of nitrogen reacts with 1 mole of oxygen, so we are getting 2 moles of NO. So the gaseous reactants are 2 and gaseous products also 2. 2 equal to 2, which means number of product molecules is equal to number of reactant molecules. So take another example. The formation of HI gas from H2 and I2. In this case also, in this example also, the gases, the number of product molecules is equal to number of reactant molecules, or you can say in terms of moles. And the number of product molecules does not equal to the number of reactant molecules. Now, is it clearly visible, the slides?
Yes, sir.
Now, instead of doing the PPTs, I have written the notes. The later I will share to you, so that this synopsis you can read and you can practice in your questions. Okay. So the number of product molecules does not equal to the number of reactant molecules. So look at this. SO2Cl2. What is its name? Any one of you? SO2Cl2. So we have SOCl2. And this one is SO2Cl2. So this is thionyl chloride. This is sulfuryl chloride. What is that? Sulfuryl chloride. So which on dissociation gives SO2 and chlorine gas. And here 1 mole dissociates into 2 moles, 1 plus 1. 2 here, 1 reactant. And this formation of sulfur trioxide. So this reaction we come across in the contact process. That is అవసరమైనప్పుడు అన్మ్యూట్ చేయండి అమ్మా. మ్యూట్ చేయండి. Contact process, manufacture of sulfuric acid. So this is the principle in manufacturing of sulfuric acid by contact process. 2SO2 plus O2 gives 2SO3. That is sulfur trioxide. Here also the reactant molecules are 3, the product molecules are 2. And the third one is phosphorus pentachloride decomposition, which gives PCl3 and chlorine gas. So in this case also, the number of product molecules are not equal to number of reactant molecules. So look at that, the delta N again, as I told. So when delta N equal to 0 for the reaction, suppose A plus B gives C plus D, which are all are gases. So we can write Kp equal to Pc into Pd, partial pressure of Pc and the partial pressure of D by partial pressure of A into partial pressure of B. And for this reaction, so here this is an important relation or a derivation. You need not to remember all this derivation. Simply just I have written that for understanding. So Kp equal to x square by A minus x into B minus x. So let us see this one. So number of reactant molecules are equal to number of product molecules. Number of moles at initial time, let it be A, B and 0, 0. And the number of moles at equilibrium, which means X moles, C and X moles of D are formed. Then the remaining number of moles of A is A minus X. The remaining number of moles of B is B minus X. Then total number of moles at equilibrium is A plus B. Isn't it? Then partial pressure of A is A minus X by A plus B into P. And for B, B minus X by A plus B into P. That is total pressure. And coming to the C, X by A plus B into P. That is a partial pressure of C at equilibrium. And the fourth one is X by A plus B into P at equilibrium. Now what is Kp? Partial pressure of C into partial pressure of D. This into this one. So X by A plus B into P whole square. Divided by partial pressure of A is A minus X by A plus B into P. And B minus X by A plus B into P. So by simplifying, we'll get a X square by A minus X into B minus X. That is a general equation for calculating Kp when delta n equal to 0. And when delta n is positive, let us see that one. This general reaction. A gives B plus C, which means delta n equal to 2 minus 1, 1, positive. So for this, Kp equal to partial pressure of B into partial pressure of C by partial pressure of A. Now, similar to earlier equation, we can reduce the Kp equation. Look at this one by one quickly. Number of moles at initial time is A, and for B and C, there are no moles initially. But at equilibrium, if X moles are formed, then the remaining moles of A is A minus X. So total number of moles at equilibrium is A minus X plus X plus X. So we'll get A plus X. Then partial pressures at equilibrium, A minus X by A plus X into P for A. And for B, X by A plus X into P. And similarly for C, X by A plus X into P. So by substituting these values in Kp and simplifying, we'll get a Kp equal to X square by A square minus X square into P. This one is Kp equal to X square by A minus X into B minus X. And this one Kp equal to X square by A square minus X square into P.
Sir, number of
Number of
equilibrium, sir. A minus X ఎట్లా వస్తుంది సార్?
ఇక్కడ ఏదా?
లేదు సార్, ఇప్పుడు the number of moles of T is equal to 0 కింద number of moles of equilibrium ఉంది సార్. A minus X చేశారు, ఎలా వచ్చిందని?
అదే ఇక్కడ ఇనీషియల్ లెట్ ఇట్ బి ఏ అండ్ బి ఇనీషియల్ టైంలో
ఓకే సార్.
రియాక్టర్స్ తీసుకోగానే ఏబి అనుకున్నాను. ఏ యొక్క మోల్స్ ఏ, బి యొక్క మోల్స్ బి. ఇనీషియల్ గా ప్రొడక్ట్స్ ఉంటాయా?
ఉంటాయి సార్.
ప్రొడక్ట్స్ ఏర్పడవు కదా, కొద్ది టైం తర్వాత ఏర్పడతాయి. కాబట్టి వాటిని ఏమనుకుంటాము, జీరో అనుకుంటాం. అండ్ ఆఫ్టర్ సమ్ టైమ్, దట్ మీన్స్ ఆఫ్టర్ ఎట్ ఈక్విలిబ్రియం, అంటే కొంతసేపటి తర్వాత ఈక్విలిబ్రియం అటైన్ అవుతుంది కదా. కాబట్టి ఎక్స్ మోల్స్ ఏర్పడినాయి అనుకుంటే let x moles of C formed and x moles of D formed. Then the remaining moles of A and B ఏమవుతుంది అప్పుడు? ఎక్స్ A minus X అవుతుంది, Bది B minus X అవుతుంది. ఓకేనా? ఈక్విలిబ్రియం వద్ద ఎక్స్ మోల్స్ C and D ఏర్పడితే ఆ లెఫ్ట్ ఓవర్ రియాక్టెంట్ మోల్స్ ఏమవుతాయి అప్పుడు?
సార్ A minus X and B minus X.
అంతే, అర్థమైంది అది?
ఓకే సార్, క్లియర్. థ్యాంక్ యూ సార్.
సేమ్ దీనిలో కూడా అంతే, సిమిలర్ ఎక్స్ప్లెనేషన్.
భయ్యా ఒక 2 minutes లో ఇది ఎండ్ అవుతుంది. యాక్చువల్లీ ఇవాళ అప్గ్రేడ్ చేయనట్టున్నాడు లైసెన్స్ ని. మళ్ళీ రీజాయిన్ అవుదాం యాజ్ గా.
ఓకే,
ఓకే, యాజ్ సేమ్ లింక్ తో ఇమీడియట్ జాయిన్ అవుదాం.
రైట్. Then heterogeneous equilibria. Look at that. Decomposition of calcium carbonate, which is in solid state, which gives calcium oxide and carbon dioxide. Calcium oxide solid, carbon dioxide gas. Because the reactant and products are in different phases, hence it is called heterogeneous, and which is a reversible process. Here, the decomposition of calcium carbonate and the formation of the forward step, and when the calcium oxide carbon dioxide combines, it gives calcium carbonate. That is a reverse step. or reverse reaction. So that after some time, the rate of forward reaction becomes equal to rate of backward reaction. So basically, what is equilibrium? The stage at which the rate of forward reaction becomes equals to rate of backward reaction. You know, rate of a reactions in kinetics. You might have studied in kinetics. The rate is an important term in kinetics. Not only in kinetics, any reaction we say rate of a reaction. And similarly, decomposition of ammonium chloride, which gives ammonia gas, HCl gas. And the decomposition of ammonium hydrogen sulfide, which gives ammonia and H2S gas. So these examples are for heterogeneous equilibria. And